NIPS players. They have kind of a top number of papers every year, and Mike Jordan's group is one of the other big players. So UI has a very impressive pedigree in terms of NIPS and machine learning. UI has done a lot of great work in non-parametric Bayesian learning, and in particular he made some very nice connections between traditional language modeling techniques and their Bayesian interpretations. His made a significant contribution in the hierarchical Dirichlet process, realizing that if you make the parent model itself atomic, then you get this very nice sharing. So I think that's a really amazing intellectual contribution amongst other things that he's done. So he's going to tell us about some of the work he's done in documented language modeling, but he has tons of various things that he's done, which you can find all the papers on the web pages and everything. And he'll be around this afternoon if you want to join us for lunch or meet with him. Just let me know. So,
okay.
Take it away, Yee Whye.
Okay, thanks, Sam.
Should I use presentation?
Oh, yes, I should take presentation. Thank you.
Okay, so thanks, Sam. So that's a actually really nice summary of this talks. So I'll be, this is kind of, I guess the title, as the title says, is Bayesian Nonparametrics in Document and Language Modeling. And it's just going to be some of the projects which I've been working on applying some of the Bayesian Nonparametrics ideas in document and language modeling. So I think both the hierarchical Dirichlet process as well as the language modeling work will appear. That Sam has mentioned will appear here. So I presume that most people here may or may not know much about Bayesian nonparametrics, so I'm going to spend a bit of time going through some intuitions of Dirichlet processes first before I go into the rest of the talk, I guess. So the first bit is really just kind of review, I guess. So here's an overview. So I'll start off with telling you about what are Dirichlet processes and basically infinite mixture models. And then I'll talk about hierarchical Dirichlet processes, topic modeling, and language modeling. Okay. So let's start off with a very simple a problem of clustering, right? So it's kind of one of the basic problems of machine learning. You're given a set of data points, and you want to figure out which are the subsets of your data points which are similar to each other and different from other subsets. Right? So those are the clusters of your data points. And this is, of course, a basic technique that's been used, that is used all over the place in machine learning, data mining, statistics, right? And of course, it's a really rich history of, with many algorithms and models applied, proposed for clustering. Okay. So there are kind of two algorithmic questions, I guess, for clustering. The first one is, where are the clusters? If you're given a data point, you're given a data set, where are the clusters? Okay. So in this case, you might think that, okay, there might be like 5 clusters here, 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 and here, for example, right? And the second issue, which is kind of a harder issue, is how many clusters are there, right? So if I give you a, if I give you a data set, how do you determine the number of clusters in this data set? So for example, in this case, maybe you might think that there's 5 clusters, but if in the future you see more and more data points and you see that there's lots of data points in here, and then there's lots of data points in here, and there's some sort of margin in between the two, then you might think that maybe it's not 5 clusters, maybe it's 6 clusters. Okay. So this is a question of model selection. How do you select for the right size of your clustering model to explain your data well? Okay. So the approach we should take for clustering is mixture models. So this is a probabilistic approach to clustering. So given a data set, say x1 until xn, okay, so the probabilistic approach says that you start off with some description of how is it that the data could be generated based on some set of parameters. Okay. So in the case of mixture models, you assume that the way the data set is generated is the following. For every data point, you pick a cluster from some distribution over clusters, and then given the cluster which the data point belongs to, you then generate the actual data point itself based on some distribution that describes the cluster. So in the case of Gaussian clusters, for example, the parameters, each cluster is described in terms of its mean and its covariance. So those would be the parameters of your mixture model. Right? And given this generative process, you can then write down what's the probability of your data set given your parameters. So that's, in this case, is something like this, where the pi's are your mixing proportions or the prior probabilities of your data point being assigned to each cluster. And this p of xi given, so zi is a cluster indicator variable which tells you which cluster data point xi belongs to, and theta zi is your cluster parameters, and p of xi given z and theta is the probability of that data point given that cluster. Okay. The typical approach for mixture modeling is to find the parameters which maximize the probability of your data. Which maximizes the probability of the data. So this is called the maximum likelihood approach. And I think probably a lot of people here would know about maximum likelihood approach. So I won't really go into it. So, and I guess I should say that, so once you've found a maximum likelihood set of parameters, that kind of tells you where are the clusters. Okay? So the second question we should like to ask is, how do we determine the number of clusters? Right? If you just do maximum likelihood, what happens is that as you increase the number of clusters in your mixture model, you're increasing the number of parameters that's used to describe the data. So you're giving the model more and more flexibility in terms of describing the data. And of course, the probability of the data would always increase as you increase the number of clusters. Right? So this would lead to overfitting. If you just say you just want to find k, so the number of clusters which maximizes the probability of the data. So people have dealt with this, for example, by using cross-validation or using some sort of external measure of the fitness of the mixture model. So for example, if you use your mixture model to, if you have a second stage in which after you've clustered your data, you might want to do some sort of discrimination task, then you might want to optimize for the error after you've clustered your data. Right? So in this talk, I'll be taking a Bayesian approach, and what the Bayesian approach says is that you actually want to account for the parameters of your mixture model by introducing a prior which regularizes them. Okay, so the prior you can think of it as every time you introduce new parameters into your mixture model, you want to pay a cost for the parameter, right? And because you have to pay a cost for the parameter, as you increase the number of parameters or your number of clusters, at some point there's this trade-off between paying lots for your parameters and describing the data better. And at some point, the trade-off will kind of balance out, and it's that point in which you have the optimal number of clusters, according to the Bayesian approach. And given a prior, you want to compute a posterior distribution over the parameters and your latent variables. Right? So this is given by Bayes' rule. And if you compute this posterior distribution in a proper manner, you're not really fitting anything to your data, right? So, and what this means is that, in a sense, the Bayesian approach does not really overfit your data at all. Okay, if you do it properly, of course. And since the Bayesian approach doesn't really overfit to your data, there's really theoretically no reason to use small models anymore, because you like your model to be as rich as possible to describe any data set that you could encounter. Okay, but so if you deal with small models, you may have a problem of underfitting, right? So you want to avoid that by using large models, and the Bayesian approach does not overfit, hopefully, right? Okay, so which means that we can consider mixture models with basically really large number of clusters. So these are what's called infinite mixture models, and it's been proposed by in the machine learning community by Radford Neal and Carl Rasmussen. It's in statistics, people have looked into this for kind of a longer period of time, and it's got a richer history, I guess. And the idea of an infinite mixture model is that you define a finite mixture model, given here, and then you say that let's just assume that the number of clusters in our mixture model is really large. So we take k, the number of clusters, to go to infinity. Then the next question is, what does this infinite limit actually mean? Right, I'll come to that later, but I'll kind of describe the mixture model as given here just to familiarize you with the notation I use. So pi here is a mixing proportion for your mixture model. Okay, and usually we give a prior over mixing proportions, which is a Dirichlet distribution. Okay. And this is usually because the Dirichlet is kind of a very nice conjugate prior for mixing proportions. Basically, allows you to do computations in a very tractable manner. Okay. And being Bayesian, basically you do want to introduce priors for all your parameters. So theta k is the parameter for cluster k, and let's assume that they are drawn IID from a prior over parameters given by h. Okay. And then for each data point xi, we have a corresponding latent variable zi, which is its cluster indicator variable. It tells you which cluster does data point xi belong to. And this is drawn from a multinomial distribution with parameters pi. And then xi given zi and the cluster parameter theta is drawn from some distribution f parameterized by theta. Okay, so this is the notation I use, I guess. So, and this is a corresponding graphical model for the mixture model. Okay, so coming back to here, what does this infinite limit mean? Okay, so there's kind of a few ways of looking at what does this infinite mixture model mean. So philosophically, what this thing actually says is that it's basically encoding a prior belief that the data that we see in the real world is often coming from very complex processes that cannot really be described by very simple finite mixture models. Right? It's a complex process requires a complex model, basically. Okay. Algorithmically, this infinite limit can be seen as basically an infinite limit of algorithms for posterior computations for the mixture model. Okay, and so I think both Radford and Carl, they came about this idea of an infinite mixture model from this algorithmic perspective. Okay. But what of the model itself? What is the infinite limit of the model? Okay. And it turns out that this is basically a stochastic process called the Dirichlet process, which has been studied in the statistics literature for the last basically 35 years now, I guess, for maybe 40 years. Okay. So next few slides, I'll tell you what are Dirichlet processes. So what's a Dirichlet process? So it's basically a distribution over distributions. Okay, and so I kind of write a Dirichlet process in the following way. So G is a random distribution that is Dirichlet process distributed. Okay, and it has two parameters, the Dirichlet process. It has a concentration parameter, alpha, and a base distribution, h. The base distribution, you can think of it as the mean of G, and alpha is some sort of inverse variance for G. Okay, so just as a Gaussian, you parameterize it with a mean, and variance, in this case a Dirichlet process, you parameterize it with a base distribution, which is basically the mean, and alpha, which is the inverse variance. Okay, and what is meant by a distribution over distributions? What's meant is that if you draw a sample from a Dirichlet process, then the sample itself is a distribution. So G is a distribution. Okay, and in particular, it turns out that a draw from a Dirichlet process is always going to be a discrete distribution. And a discrete distribution is simply a distribution which consists of a number of atoms. Okay? And you can always write it in the following ways. It's going to be an infinite sum of weighted atoms. So delta theta k is an atom located at theta k in a probability space, and pi k is the weight of the corresponding atom. Okay. Of course, since G is a distribution, the weights has to be non-negative and sum to 1. Okay. So the pi's are non-negative and sum to 1. And I haven't really told you what are the distributions corresponding to. So G is random, right? So which means that both pi and theta are random. I haven't really told you what are the distributions corresponding to theta and pi. So for theta, it's very straightforward. Each atom in your Dirichlet process are simply IID draws from the base distribution, h, given here. Okay. While the pi's are coming from a stick breaking process it's what's called a stick breaking process. And kind of the basic idea is very simple. So imagine that you have a stick of length 1. So for some reason, the Dirichlet process literature has a lot of kind of metaphors like stick breaking constructions and Chinese restaurant processes and stuff like that. So you see the Chinese restaurant process later on. Here I'll tell you about the stick breaking process. So for the stick breaking construction, you start off with a stick of length 1, and you break it at some point, say here. Okay. So the length of this bit of the stick now is going to be your pi 1. Okay. And then you take what's left of this stick, okay, and you break it at some point again, here. And the length of this segment now is going to be pi 2. And then you kind of break it infinitely often down this way. And that's going to be pi 3, pi 4, pi 5, pi 6, and so forth. And if you start off with a stick of length 1, the sum of the pi's has to be 1, right, by definition, basically. And yeah, so that's basically the stick breaking construction. So that gives you a way to construct a sample from a Dirichlet process. You draw your pi's using this stick breaking construction, and then for every atom you draw IID from your base distribution H. Okay, so that gives you a constructive definition. So how do we use this in a mixture model? So if you have your G, which is drawn from a Dirichlet process, we know that it itself is a distribution, so we can draw samples from it. So let's draw a bunch of samples, phi I from G. Okay. Then for every data point xi, we are going to say that xi is going to be drawn from some distribution which is parameterized by phi I. Okay. Now, since G is a discrete distribution like this, that means that phi I is going to take on value theta k with probability pi k, right? So that's the definition of a discrete distribution, basically. And if you now say that, let's just say that data item I is going to be assigned to cluster k if phi I takes on value theta k, right? Then you see that this Dirichlet process mixture model is basically a mixture model with an infinite number of components, each component corresponding to one of the atoms in your Dirichlet process. And the pi's correspond to your mixing proportions, and theta k corresponds to your parameters of your mixing to the parameters of your clusters. Okay, so this is a kind of a very nice way of describing a mixture model with an infinite number of components, basically. Okay, and it turns out that it's equivalent to this infinite limit that I've kind of described here. Okay, of an infinite limit of finite models. Okay, okay, so that's basically a Dirichlet process, and a Dirichlet process is basically one of the cornerstones of Bayesian Nonparametrics. It's one of the basic models that everybody uses. And some, I guess, philosophy of Bayesian Nonparametrics. Firstly, I've kind of told you that basically real data is often very complicated, and really no parametric model is suitable for describing this real data. So you do want to move to non-parametric models. A second reason for using non-parametric models is that if you use parametric models, you often have to contend with this issue of model selection. So in the case of mixture models, how many mixture components are there and stuff, right? Turns out that model selection is a very hard question if you look into the literature, and non-parametric models basically sidestep this issue at basically little extra cost. Okay. I have to kind of say two caveats, I guess. Firstly, that non-parametric models are never really truly non-parametric, right? Often what people do is that they start off with some parametric model, and they fit it to their data, or and then they find that, okay, perhaps it doesn't really fit the data very well. So then you could kind of like make it richer by non-parametrizing certain aspects of your parametric model that does not fit the data well, right? And this often results in models which can basically be said as semi-parametric because it has certain components which are parametric and certain components which are not parametric. Okay, and a second note caveat is that because non-parametric models are kind of very rich models, sometimes if you're not careful, you may end up with models which are basically not consistent, and you have to be careful that in your applications of non-parametric models, that they kind of work well for the problem that you look at. Okay. So I'll move on to hierarchical Dirichlet processes now. Right, so for Dirichlet processes, I've just motivated it as clustering of one single set of data points. Right. So for the hierarchical Dirichlet process, the corresponding basic problem is still clustering, but you're clustering multiple groups of data points, but such that the groups of data points are somehow related to each other. So here, for example, we have 3 groups of data points, and say you might think that there are, say, 3 clusters here, maybe 3 clusters here, and 2 clusters here with some outliers. Okay. And what I mean by related is that the clusters in the different groups of data can be shared across the different groups of data. Okay, so if you so you might fit mixture models to these 3 groups of data, and you find that, say, this cluster is basically the same as that cluster. It's basically the same as that cluster. Okay, so basically we have multiple groups of data. We want to cluster each group using a Dirichlet process mixture model, because we also want the model to discover for us the number of clusters that's exhibited in each group. But at the same time, we want our clusters to be shared across these multiple groups of data. Okay. So just to motivate for you some examples of how this clustering of related groups of data appear in applications. The first one is in topic models. So if you're familiar with latent Dirichlet allocation, which is a very popular topic model, a model for describing documents in terms of sets of topics, you take a document, right, and you, which is basically a sequence of words, and you treat it as a set of words in which the ordering doesn't matter, and then you model the document with a mixture model, where each component of the mixture is a topic. Okay. So here, say I have 3 topics, and I've kind of like highlighted the words in different colors corresponding to the possible topics that the words could belong to. Okay. And of course, you never have one document, you often have lots of documents, so you have a corpus of documents, and you want to describe each document with a set of topics, but the topics are shared across documents. Right. So now you have, for every document, you have a group of words. You want to cluster the words together, such that the clusters or the topics are shared across your groups of words on your documents, and you want to also discover the number of topics. So that's precisely the problem which I've just described here. Right. So this is in document modeling. In genetics, this sort of problems has also occurred in. So for example, you might have multiple populations of individuals, and you might want to cluster the individuals into different clusters based on their genotypes. And of course, populations are never the same, so different populations might have different proportions of the different types of the different genotypes in the human race, I guess. So again, we have, for each population, we want to cluster individuals into different genotypes. The genotypes are shared across multiple populations. Okay. And we also want to determine the number of genotypes. Another example of this problem occurs in visual modeling. So imagine that you have multiple images. You've extracted certain descriptors from each image. Now you might want to cluster the descriptors within each image into the different objects in that image. And objects could again appear in different images, and different images could consist of different sets of objects. So this is again this problem of clustering of related groups of data, each group corresponding to an image now. Okay. So how do we solve this problem of sharing of the clusters across this grouped data? Okay. So in the statistics literature, sharing in group data is often addressed using this notion of a hierarchical Bayesian model. Okay, so the simplest kind of example of a hierarchical Bayesian model is that let's imagine that you have two groups of data. This is group 1 and this is group 2, and you might want to figure out, estimate the mean of the data points in each group. So this is going to be the mean for group 1, a mean for group 2. Okay. And if you believe that these two groups are related in the sense that the two means are somehow related to each other, the way you do it is to say that both means are random, and they come from, say, a Gaussian with a common mean, a global mean. Okay? And this global mean, mu naught, is itself a random variable. And because mu naught is random, it would induce dependencies across the means for the two groups, right? And it's precisely this dependency which describes the sharing of the information across these two groups of data. Okay? In the case of the hierarchical Dirichlet process, it's basically a hierarchical Bayesian model that shares clusters across the different groups of data. Okay. So as I said, so we want to cluster, the data points in each group using a Dirichlet process mixture. So here is a simple example in which you have two. For group 1, you might have a draw from a Dirichlet process G1, which kind of gives you a Dirichlet process mixture to model group 1. And then for group 2, you might have a separate Dirichlet process G2, which gives you a Dirichlet process mixture for group 2. Right? So you might make this into a hierarchical Bayesian model by saying that the common parameters of the two Dirichlet processes, so the base distribution and the concentration parameter, you can induce sharing of information across these two groups by letting both of these be random variables. Okay. But the problem with this approach is that if our base distribution is a smooth distribution, then we will never get clusters shared between the two groups. And we can see this because recall that in the Dirichlet process, the atoms in the Dirichlet process are drawn from IID from the base distribution, right? So we have a set of clusters here which are drawn IID from H. You have another set of clusters here which are drawn IID from the same H. But if H is a smooth distribution, then if you draw a bunch of samples from H here and a bunch of samples from H here, these two sets of samples will never overlap with each other, right? Because that's basically the definition of a smooth distribution. Right? It doesn't have atoms, basically. It's non-atomic. And if the atoms don't line up, and we know that the atoms in the Dirichlet process correspond to clusters in our mixture model, then the clusters will never be shared because the atoms are not shared. Okay. So the basic idea here is that if we make the base distribution discrete, then the atoms will be shared. Okay. And this is basically what we do in a hierarchical Dirichlet process. We simply say that the common base distribution of our two Dirichlet processes, so both G1 and G2 are now going to be drawn from a Dirichlet process, the same Dirichlet process with a common base distribution of G0. And we again place a Dirichlet process on top of G0. Okay. And because G0 is a draw from a Dirichlet process, and we know draws from a Dirichlet process are discrete distributions, the atoms in G1 and G2 will be precisely the set of atoms in G0. Okay. And that's how clusters are shared across the two groups. So visually what happens is to draw a sample from this model, right, G0, G1, and G2, we draw from G0 first. That gives us a set of atoms. And we know that the set of atoms in G1 are drawn from G0. So it has to be one of the atoms in G0. So the set of atoms here is precisely the same as the set of atoms here, which is also precisely the set of atoms here. Okay. So we have exactly the same set of clusters which are shared in the two groups, but the mixing proportions, which corresponds to the weights, will be different now in the two groups. Okay, so that's basically the hierarchical Dirichlet process. In general, a hierarchical Dirichlet process is basically a set of Dirichlet processes which are linked together in a hierarchical manner. Right? So you have a tree structure over multiple Dirichlet processes, and each Dirichlet process has a base distribution given by its parents in the tree, basically. Okay. And it turns out that there are analogs of the stick-breaking construction, which I kind of briefly described in the Dirichlet process. There's an analog for the stick-breaking construction for the hierarchical Dirichlet process. I haven't really told you what Chinese restaurant process is yet, but there's also analogs for that in the hierarchical Dirichlet process. Okay, so that's a hierarchical Dirichlet processes, and it's kind of used. It seems to be used across quite a number of different domains by now. So I'll tell you actually an application of the hierarchical Dirichlet process to topic modeling, which actually is one of the motivations for when I started looking into hierarchical Dirichlet processes. Okay. So recall that the problem we want to solve in topic modeling is that we have multiple documents, and we want to describe each document in terms of a set of topics. Basically a mixture of topics. Okay. And the most popular model for documents is basically probabilistic LSI, as well as latent Dirichlet allocation. Okay. And the model which we look at is an extension. You can think of it as a non-parametric extension of LDA, or latent Dirichlet allocation. So this models each document as a finite mixture model, okay, where the topics or the classes are shared across the documents. So each document has its own mixing proportion. We're going to give each of the mixing proportions a Dirichlet prior again. So this is given by this. And we have a number of topics, and each topic has a set of parameters theta, which is also given a Dirichlet prior. Okay. And then the generative model for LDA is that for every word, we're going to first pick a topic that's given by ZJI. And then given the topic, we're going to draw the word itself given the topic. Okay. And this is a very successful model with lots of different extensions of it. And the particular extension which we look at here is that we run a non-parametric extension in which we have an infinite number of topics. Okay. I'll skip this. So the HDP can basically be directly applied to produce a non-parametric LDA with an infinite number of topics. Okay. So here, each document has its own Dirichlet process. So for document J, we have a draw from a Dirichlet process given with a base distribution of G0. And then for every word in the document now, we're going to first draw a topic from GJ, and then we're going to draw the word given the topic. So this is quite similar to the LDA bit. The difference is that the GJs are draws from Dirichlet processes, so they have an infinite number of atoms. So we actually have an infinite number of topics here. Okay. And now, to induce sharing of the topics across our corpus, we'll simply say that the base distribution G0 is itself going to be random and be drawn from some Dirichlet process, some global Dirichlet process. And the base distribution for this Dirichlet process is basically the same as the prior over the topic parameters in LDA. Okay. Okay. So we kind of you can compare the non-parametric LDA against a parametric LDA in terms of perplexity. Okay. So here I've run the HDP topic model on a corpus. This is a NIPS corpus. No, this is not a NIPS corpus. It's the nematode corpus, I think. And it produces a certain perplexity. So that's given by the red line. Okay. For LDA, it's a parametric model, so you need to tell it the number of topics that it uses to model the corpus. So we vary the number of topics in the x-axis here. And you can see that as you vary the number of topics, it kind of produces a U-shaped curve in which the perplexity is lowest in this regime, right? And you can see that the HGP is basically doing just as well as the best LDA model, but we don't have to do any model selection for it. Okay. So it's kind of, in fact, more efficient if you take model selection into account here.
So I'm skipping back to the previous slide and just so the phi j i's are drawn from. Let's see, where am I drawing this?
From
the GJ.
GJ, yeah.
Let's see. Now GJ is just for that particular document.
Yes.
So I'm kind of missing a little bit. I can see how that gives me this. What I'm not seeing is the word distribution. Each topic, the topics are shared across
Yes.
all documents, right?
Mhm.
So and that draw there is just. So there's something. It gives me the impression that you're abbreviating something here, right?
Okay.
The feed. I would think the feature as a fixed in a sense across all documents.
Sorry, facts.
Fixed. It's
Fixed.
just the choice, the probability of selecting a particular one for a particular word varies from document to document
Yes, yes.
according to GJ.
Yes, that's right, yeah.
So it's not the feed J I'm drawing from GJ, right? It's just the mix is the
topic
the
indicator.
index.
I see.
Is
So
or am I confused here?
yeah, so so the phi ji here is actually not the index, but it's actually the parameters of the topics itself. Okay. So recall that so here's the funny thing with the Dirichlet process is that in a typical mixture model, you think of the mixing proportions and the cluster parameters as separate things, right?
Yeah.
You first pick your cluster according to the mixing proportions, and then you you generate your data according to the parameters given from the corresponding cluster. Okay. In the Dirichlet process, they're kind of like, they are tied together. Okay. So recall that if you have a draw from a Dirichlet process, is this infinite sum, right, of delta functions here.
Right.
Right. So this is a draw from your Dirichlet process.
Right.
It has weights and it has atoms. The atoms corresponds to the parameters of the clusters, and the weights correspond to your mixing proportions. So if you draw a phi from G here, right, phi is going to take on one of the values of theta k. Okay. Right. So it equals to theta 1 with probability pi 1 equals to theta 2 with probability pi 2, theta 3 with probability pi 3, and so forth. So the pi's are the mixing proportions, but the thetas corresponds to the parameters of the clusters. So when it takes on the value of the parameter of the cluster, we can then, so that's precisely what happens here.
Can I ask another question? So
Yeah,
when you
here.
give this prior and the base distributions, it looks like there's this W that.
Yeah, so that's
Is
actually,
that a parameter you have to select?
oh, that's simply the vocabulary size. We're kind of like assuming that we have a finite vocabulary, and the betas are the kind of the pseudo counts for the words, for the word types across the corpus. Basically. Usually people just take the betas to be all the same. Okay. In fact, beta over W. Yeah. Okay. So it's kind of like rolled into one. So phi ji is going to take on value theta k, and what that means is that word xji is going to be assigned to topic k, and phi ji itself is going to be the parameter for topic k that's going to be used to generate the particular word x. Yeah.
I have another question.
Yes.
So because here the Dirichlet, the base is defined on the W, the vocabulary, so it's a finite. So
Yes.
that seems the G0 is not going to be an infinite sum.
It is
finite.
no, it's actually an infinite sum here because this is so this Dirichlet, right, is a finite dimensional distribution, but it's still a smooth distribution. So you could still have an infinite number of different atoms drawn from the smooth distribution. Right? So in the language modeling case later on, it will turn out to be finite. Okay, so I guess we should move on quickly. We can also generalize this hierarchical Dirichlet process topic modeling to the case where we might have multiple collections of documents, and we want topics to be shared across documents within each collection and also across collections, but of course we want the sharing within each collection to be stronger than across collections. And the hierarchical Dirichlet process can basically be generalized to this case in basically a straightforward manner. So you would have a different Dirichlet process for each collection. You have a global Dirichlet process which ties together all the collections, and then you have a separate Dirichlet process again for each document in each collection. Okay, so I'll skip that bit. Basically it does well. Actually it's kind of interesting to see some of the topics which could be shared across different collections. So this is in the NIPS corpus, and you can see that, for example, the topics which are shared between vision and signal processing tend to be, actually this first topic is a bit funny, but if you look at the second topic, it's kind of like image processing type of words. Okay, and the topic which is shared between vision and neuroscience tend to be about visual neuroscience, like the visual cortex and stuff like that. So it's kind of nice. And as I said, so the HDP has been applied. Well, I guess there are two things here. The first thing is that there are also other non-parametric extensions of LDA. Here I've listed two of them. So there's nested Chinese restaurant process and pachinko allocation. The HDP has also been used in genetics. So this is a haplotype inference problem by Eric Singh. It's also been used in time series modeling, where we have a generalization of the hidden Markov model, where you have an infinite number of states in your hidden Markov model. And it's also been used in vision. So the visual modeling example that I gave you, the image, I just cropped out from Eric Suther's paper. Okay. Right, so I want to move on to language modeling in the last 15 minutes of the talk. So this is kind of interesting because there are two ideas in the hierarchical Dirichlet process. This hierarchical models, and then the second one is, of course, non-parametric models. And it turns out that both ideas can also be used in language modeling. Okay, so the language models which I'll deal with here are n-gram language models. So basically model a sentence using, you want to build a distribution over sentences where the probability of a sentence is simply a product over the probability of each word given its context, which is a fixed length of words which appears right before the word of interest, word I. Okay, so we predict word I given words I minus n plus 1 until word I minus 1, basically. Okay, and of course, I think everybody here knows that if you have for most of the natural languages, we have a large vocabulary, and you cannot estimate the parameters using in a naive manner. I think maybe Google was able to do it recently, I think. Yeah, treat this as a 2-year-old slide. So if maximum likelihood estimation doesn't work, it turns out that naively regularizing our parameters don't work as well. And the reason is because most of the parameters, in fact, will have no associated data at all. Right? So, and then basically it will just simply reflect our prior, which may not be very good if you have a naive prior. And basically, there's a kind of a really rich literature on the problem of smoothing, which is a way of dealing with this sparsity of language models, of data associated with language models. And smoothing is basically the basic idea is that you want to interpolate, or you want to average between larger and smaller models, so that the larger models are able to give you the expressiveness, and the smaller models you can kind of like back off to the smaller models when you do not have enough data to estimate your large models well. Okay. I'll skip this bit. So and it's a really rich literature, and So I guess Chen and Goodman did a really nice review of the state of the art of smoothing algorithms, I guess 10 years ago. And they have found that interpolated Keynesian and modified Keynesian are the kind of the best smoothing algorithms that they had so at the time, right? So in this part of the talk, I would like to look into a Bayesian approach for smoothing, and the reason for this is that this idea of smoothing is really similar to this idea of hierarchical Bayesian modeling, which I've just described, because you can think of each context in your language model as a different group of data, and then you want to share information across different groups, right? And you can use a hierarchical modeling for doing that. Okay. And specifically, the hierarchical model which we'll build is based on a tree of suffixes. Okay. So what this means is that we assume that the more recent words in the context are more important, which kind of is reasonable. And the second idea in this is that we'll be using a generalization of Dirichlet processes called Pitman-Yor processes as the priors instead. So we'll be using hierarchical Pitman-Yor processes. Okay. And the reason for this is that Pitman-Yor processes produce power law type of behavior, which are much better models for languages than the Dirichlet processes are. Okay. And the nice results here is that firstly, we do produce state-of-the-art language modeling results. And secondly, in fact, we can show that interpolated Keynesian can be interpreted as approximate inference in this hierarchical Pitman-Yor language model. So this is kind of nice because it gives us a nice explanation for why is it that interpolated Keynesian does so well. So what sort of hierarchical model do we do? So I said that we'll be using suffix trees. So here's a kind of a little example. So we might have different contexts, say hidden Markov, right? So that's our context. We want to predict the word model. Okay. So for different contexts, U, we have a vector of probabilities for the words which could occur after that context. So G of U of W is simply the probability that word W occurs after a context of U. So this is G hidden Markov of model. Okay. So of course these things are probability vectors, so they have to be, each entry has to be non-negative and they have to sum to 1. Okay. So we have lots of different contexts, right? Because for every pair of words here, for every sequence of words, we have a different probability vector, and the hierarchical model which we place on this set of probability vectors is basically the following, where as you go up the hierarchy, you drop the initial word from each context. Okay. So in this case, G hidden Markov and G stationary Markov both have the same parent, which is G of Markov, okay, and so forth. And basically, you can think of G of Markov as the mean probability vector in a prior for both of these probability vectors. Okay. And basically, in this hierarchical model, there is sharing of information across the different contexts on the tree, right? And the structure of this sharing is precisely the same structure of sharing that we see in the traditional smoothing algorithms. So the next question is, what are the distributions that's going to be placed on each of these edges? So what's the distribution over G of hidden Markov, given that its mean is G of Markov, right? So what is probability of G of U given G of parent of U? Okay. So the standard distribution that people use on probability vectors is of course the Dirichlet distribution, and this produces a hierarchical Dirichlet process language model, okay, in this case. And Mackay and Pito has proposed that like about 14 years ago now. But it turns out that this is a bad model for languages. So here's just an example. I have kind of varying training set sizes and different context lengths, and this is interpolated Keynesian, and the numbers are the perplexities, so lower is better. And this is modified Knason A. So these numbers are pretty good, and the perplexity for the hierarchical Dirichlet language model is a lot worse, right? So this is kind of a bit unfortunate, because I think this idea of hierarchical Bayesian modeling is really well suited to language models, but you know, because it didn't do as well as interpolated Knason as a lot of the other smoothing algorithms, people kind of like gave up on the Bayesian approach to language modeling for like 10 odd years, I guess. And it turns out that the problem here is that the Dirichlet distribution does not produce power law type of behavior which fits in with languages very well. Okay, and we'll be extending the Dirichlet process to Pitman-Yor processes. So to see how is it that the Pitman-Yor process extends the Dirichlet process, we will be talking about the Chinese restaurant process. So this Chinese restaurant process is basically a different perspective on the Dirichlet process, and it gives us a distribution over partitions. Okay, so it's a Chinese restaurant. So we imagine that we have a. Okay, so now here's a different metaphor. Okay, so we have multiple tables in our Chinese restaurant. In fact, we assume there's an infinite number of tables. Okay, and customers come in one at a time, and they sit around tables. So the first customer sits at the first table. The second customer could choose between sitting with the first customer or at a new table, and then the third customer could choose between sitting with the first customer, the second customer, or at a new table, and so forth. And all the customers come in and sit around tables like this, and basically the first customer sits at the first table, and subsequent customers will sit at table K with probability proportional to the number of customers sitting around table K at a time, and will sit at the new table with probability proportional to a parameter alpha. Okay. So what this produces is that if you have like 9 customers, if you have 9 customers, this produces for us a partition of 9 customers into multiple tables, right? So if you think of customers as data points and tables as clusters, this produces for us a distribution over clustering of data points. And now for each table, we can associate a parameter for the cluster, okay, which we can draw from a base distribution H, and then the corresponding data point xi will be simply drawn from some distribution parameterized by the cluster parameters. Okay. So this gives us basically a Dirichlet process mixture model. Okay, so this is for a Dirichlet process. What's the difference in the Pitman-Yor process? The difference is simply that when a new customer comes in, the customer will sit at table K with probability now going to be proportional to the number of customers sitting around table K. Subtract away a discount factor. This is a fixed parameter that's between 0 and 1. Okay. And the new customer will sit at the new table with probability proportional to alpha plus dk. So we have k tables, and we subtract probability mass of d from each table, and we're going to add all of those probability masses to the probability of the customer sitting at a new table. Okay. And this is of course a generalization of the Dirichlet process, which is the case when d equals to 0. And why does this work? The reason is because for the Dirichlet process, we have the probability of sitting at a table K is proportional to the number of customers sitting around that table, right? So it has this rich gets richer effect. So this tends to produce for us a few tables with lots and lots of customers, right? So you can think of this as there are a few word types which are really common in examples of a language. So these are basically the common words in a language. So things like stop words in that particular language, they are very common, right? But for the Pitman-Yor process, it has this second effect in which if we see lots of words coming, if we see lots of different tables, then the probability of the customer sitting at a new table also increases. And this corresponds to the effect where in lots of languages we have lots of words which all of them all of which occur really rarely, but there's lots and lots of them, right? So basically, there's two effects here. One is that there's a small number of common word types, and the second effect is that we have a large number of rare words, right? And this, in fact, produces a power law type of behavior, which is, of course, more suitable for languages because it does correspond to languages pretty well. So just to show you some graphs, so here I've plotted the number of unique words we see as a function of the number of word tokens. Okay, so, and for the Dirichlet process, this kind of tapers off after a while, but for the Pitman-Yor process, it increases a lot faster than the Dirichlet process.
So, I mean, are you? I can't remember this. Are you assuming an infinite? The model here also has infinite number of words.
You could actually assume that, but in the applications in the experiments which you see, which I will show later, I assume a finite vocabulary, but it still has this effect where it tends to like seeing lots of rare words as compared to the Dirichlet process.
Right.
Yeah.
There's sort of something a little bit unsatisfying about that, right? Because if I just looked at 1 year of news and now I look at the next year of news, there's going to be some new words.
Yes. Yeah.
So some of this
Right. So it is definitely possible to extend this to the case where you could generate an infinite number of words from. So you just have to make sure that your base distribution itself can generate an infinite number of words. It's just that we haven't really done that yet.
Have you tried that, or has anybody tried that?
We haven't tried that yet, but it's one of the next things that we want to do.
Okay.
So how do you pick D here?
In the experiments, we actually do two things. We try cross validation to fit D, and the second one is actually we introduce prior for D, and then we just do posterior sampling for D as well, and they work about the same. It seems that cross validation worked a bit better in our experiments, and I think that's because even though this is a more suitable model than Dirichlet processes, it's still not the perfect language model, of course, right? So I should wrap up. Okay, so basically it does pretty well. It does just as well as modified Knazen-Ney and interpolated Knazen-Ney, and in fact the numbers look very similar, and I think the reason is because you could basically treat the Knazen-Ney methods as very good approximate inference algorithms for this hierarchical Pitman-Yor language models. Okay. We've also looked into domain adaptation with this language model now. We've extended it to a graphical Pitman-Yor process. We can talk about this offline if you want, I guess. And this plot kind of shows you kind of the perplexity as you increase your training set within your domain of interest as well as some general domain, and in both axes the perplexity decreases as you increase your amount of data, and it seems to work pretty well against simple baseline. So this is still kind of work in progress. Okay. So conclusion. So I think Bayesian Nonparametrics is quite nice. Has some really nice applications in both document and language modeling, and there's in fact recent work that tries to merge both ideas together, and I think the graphical Pitman-Yor process framework may actually provide a nice framework to explore some of these ideas, merging document and language modeling. And of course I've only talked about some of the work which I've done myself, and there's Bayesian Nonparametrics is a kind of a growing field now, and it's growing pretty fast, I guess, in both machine learning and statistics. In statistics, people are interested in various processes which go beyond Dirichlet and Pitman-Yor processes, while in machine learning, it seems that people are interested more in things which go beyond clustering. And kind of they are structurally quite different. So the thing with the models that the statistics people have been looking at is that they are different priors which you can use, but they are still used for clustering. And in machine learning, people are interested in using these non-parametric models to go beyond, to do structured learning beyond figuring out the number of clusters in your data set. Okay, thank you. Yes.
Can you say a word about computational complexity, training and inference?
It's pretty efficient. So for the language modeling case, it's actually very efficient, because turns out that.
What do we mean? Linear?
Okay.
Less, more?
Yeah, I guess it is linear in your training set, so it's still not quite Google scale. But it's linear, and the nice thing with the language modeling case is that you could show that the posterior is in fact convex. It's log concave, so it's a unimodal posterior, so you can get samples from the whole posterior very efficiently. So you need only a very few number of samples from your MCMC. So for the document modeling case, it is, well, I mean, it's the same as in LDA. You have like collapsed skip sampling. It seems to be very efficient, and this thing uses collapsed skip sampling as well. In fact, I think the non-parametric models tend to be more efficient than a naive implementation of a large parametric model. And the reason is because it scales according to the number of clusters or the number of topics which are actually used by the data. While in the parametric case, the scaling is actually, it scales linearly in the number of potential clusters which could be used to explain the data, which could potentially be much larger than the number that's actually used to explain the data.
Other questions? Okay, thanks, Yee Whye. Oh, one more. All right.
So you're going to get some kind of a ZIF law with parameter 1 plus d for the word frequencies.
Mm-hmm.
And then you had another curve which was how fast new words arise. And I'm forgetting the
This
name,
one.
but there's somebody or other's law for how fast new...
Heaps law.
Yeah, so does
Heaps
it
law.
does it tie in with ZIF and heap?
Oh, I don't know about Heaps law.
Okay.
Yeah.
Heaps law just says that the number of total vocabulary items you expect to see after consuming n words is a power law itself. And there's a relationship between Heaps law and Zipf's law.
Oh, so it has to match. If you get one, you have to get the other.
Well,
So
I mean,
I
if-
guess
if
this
you-
thing is this plot that I'm showing is actually a Heaps law, I guess.
Right, that's
Yeah.
exactly
Yeah,
that's
that's what-
Heaps law.
And I guess Zipf's law says that the most popular word is kind of significantly more popular than the second most popular word, and so forth. And this thing actually appears in the Pitman-Yor process too. Yeah. But I guess they're tied because they use the same parameter d to describe both. Yeah. So I'm not sure whether you could decouple them to describe both effects separately. That turns out to be harder because turns out that the Pitman-Yor process is this really nice process, but it has two parameters, but nobody has been able to come up with the 3-parameter version of that actually has all the nice properties of Pitman-Yor and Dirichlet processes. Yeah. Okay, thank you.